Let me.
Okay.
Okay. So welcome everyone back. We are very happy to have Richard Thomas today, who is going to tell us about non-Abelian DT theory from the Abelian one. Please take it away.
Okay, thank you. Thanks for inviting me, Miroslav. So this is joint work with Sahela Feizbash. There's 3 papers on the archive proving different levels of this correspondence I'm going to describe. Non-Abelian here refers to, I mean, in physicsy language, the gauge group. So in mathsy language, there'll be bundles and sheaves, and non-Abelian will mean high rank, 2 and above, and Abelian will mean rank 1. But there'll be a rank 0 and rank -1 will make an appearance as well. Okay, so here's the plan. So I'm going to briefly review DT invariants. Not in any great depth at all. I'll just skim over it and tell you how to think about them. And then I'll focus on the rough idea of these papers, which is how to pass from rank R DT invariants to rank R-1 and below. And I'll give an example where it works perfectly and there's no corrections, which is passing from rank 1 to rank 0. So that's not really our ultimate aim. We're trying to get to rank 1. But rank 1 to rank 0 is somewhere where it just works really simply. The result is the simplest possible. So I'll explain that. And then I'll explain in general, what happens if we start in rank R, we pass to rank R-1 and below. And so we can apply that inductively. We get down to rank 1 and unfortunately rank 0 as well. So then we can go again and we can get down to just rank 0. So that'll be the first result, that we can express all rank R DT invariants in terms of rank 0 invariants. I'll say something briefly about those rank 0 invariants. And in physics, they're called D4, D2, D0 branes, and they're supposed to have modular properties governed by S-duality. So I'll say something about that. Then I'll say something about the technicalities, how we actually do this, what's involved. This will be very schematic and just pictures, basically. And then finally, I'll explain how we go from rank 0 to rank -1 and how that relates to rank 1. So ultimately, after dualizing some complexes and shifting them, we end up expressing everything in terms of rank 1, so Abelian DT theory. And rank 1 DT theory just counts curves, as I'll remind you. So you end up expressing all rank DT theory in terms of essentially Gromov-Witten invariants. Okay, any questions about that before I begin?
So you'll explain the chamber dependence of your invariants as well. This is part of the theory, right?
Sorry, what, the dependence on what, Mina?
On choice of chamber.
Yeah, that's right. That's right. Yeah. Okay, so the basic actors are a Calabi-Yau threefold, which is fixed throughout. An ample line bundle, that's for the purposes of defining stability. So we fix that. We also understand the dependence on what happens if you change that. And then an important technical condition, mainly from the mathematicians, so something that's currently conjectural but expected to be proved rather soon, is that my Calabi-Yau threefold should satisfy something called the Bogomolov-Giesecke conjecture. And I will explain that at some relevant point. And that's been proved in enough generality for us for our results on the quintic threefold. And throughout, we're going to fix a Chern character or a charge or a K-theory class of our sheaves. And we're going to consider semi-stable bundles or sheaves or complexes of sheaves of that Chern character or that class C or that charge. And the first thing to tell you about is stability, and I do this rather vaguely. So all the notions of stability we'll use will involve just some central charge, which will only depend on the topology of the situation. So just on that Chern character C. And we can take the slope of the central charge, and then basically stability always takes the same kind of shape. It says the slope of any let's suppose we're dealing with sheaves or bundles. We say that it's stable if the slope of any sub-sheaf or bundle is less than the slope of the quotient sheaf or bundle. And there's various versions, semi-stability, stability, and so on. But the important thing is what you mean by sub. So usually when you're dealing with just something called the Abelian category of coherent sheaves, so when you're just dealing with sheaves, then sub it's obvious what you mean. You mean a sub-sheaf or a sub-bundle. But in reality, it's important that we're going to work in more exotic Abelian categories. So sub is not necessarily going to mean sub-sheaf. So we're going to have complexes of bundles. Even if we only have a bundle, even if E was a bundle, it could be destabilized by some F mapping to E, but where that map is not an injection, but it is considered a sub-object in an exotic Abelian category. Unfortunately, we have to deal with this. But you can put it to the back of your mind and pretty much ignore it for most of the talk.
Can you say this again? You broke up a little bit. Even if E is a bundle?
Yeah.
At least I couldn't hear what you said afterwards.
Yeah, sorry. So even if E is a bundle, there are stability conditions where the notion of sub-object is not what you would expect. It's not a sub-sheaf or a sub-bundle. It might be, for instance, another sheaf F mapping to E, where that map is not an injection. So F might be bigger than E. It might have a higher rank than E. It might have a non-zero map to E, and that might count as an injection or a sub-object in an exotic Abelian category in which we're doing stability. So such things will arise. We're going to do wall crossing in some crazy space of stability conditions, and stability conditions like that will arise where sub-objects are not sub-sheaves. But you can ignore it and put it to the back of your mind. It really won't be important. It'll come up in one place most obviously, and I'll explain it at the time.
What will make your stability condition exotic? Like, should I think of Douglas's pi stability condition or something?
Yeah, that kind of thing. I mean, we're not quite dealing with those stability conditions, but something like that. Certainly in his pi stability, you can have an instance where a bundle, you can have pi stability conditions where a bundle can be destabilized by an object which is not a sub-bundle.
What's the simplest example?
Yeah, can I leave that for about 2 slides and then I'll give you an example. Okay, but the standard examples which aren't so exotic are Mumford stability or slope stability. So that's where the central charge, the real part is just the degree of the bundle. So the first Chern class of the bundle measured against the hyperplane class or the Kähler form. And then the imaginary part is the rank of the bundle. And so the slope is just degree over rank. And we get standard Mumford or slope stability. Oops. And then there's Giesecke stability, which is usually what has better properties for algebraic geometry forming moduli spaces. And that's given by some formula to do with the number of sections of E twisted up by a large power of the ample line bundle. But again, to leading order, it's given by slope stability, but then to lower orders, the second Chern class of E comes in and so on. Okay, but if you want to think of slope stability, if you're familiar with slope stability, which is equivalent to E admitting a Hermitian-Yang-Mills connection, then that's just fine for this talk. But we are going to vary the stability condition. All right, for now I'm going to use Giesecke stability, but it's very close to slope stability. And to start with, let's choose our charge and our Kähler form, so that there are no strictly semi-stable sheaves. So any semi-stable sheaf is actually stable. Under this simplifying assumption, which we'll drop in a minute, then it's easy to define a DT invariant, or it is nowadays. And the technical conditions you say, if you're in algebraic geometry, is that the moduli space of these sheaves is projective, and it has something called a perfect obstruction theory of virtual dimension 0. And again, the reason for that is that the obstructions to deforming a sheaf, which are given by trace free x2 from E to E, are dual to the deformations of a sheaf, so the tangent space, the moduli space, x1 E. And there's no higher obstructions because they're said dual to groups which already vanish, because E is stable, and because it's stable, it has no automorphisms except scalar multiples of the identity. So that means this group vanishes, and therefore the higher obstructions vanish. And that's more or less what means this moduli space behaves well enough to have a virtual cycle. So it has a zero-dimensional virtual cycle. So basically, you can pretend that you can perturb the moduli space until it just becomes a finite number of points. And that number of points is the DT invariant. Okay, but in physicsy terms, this is essentially saying that holomorphic bundles are critical points of a holomorphic Chern-Simons functional, and you expect critical points to appear in dimension 0. All right, so being a critical point means you're the critical locus is the vanishing of D of the Chern-Simons functional. So that's a one form, closed one form. And so, but it's it's imposing the same number of equations as there are unknowns. If you're on an n manifold, it's a one form or a vector field is like imposing that vanish is n equations in n unknowns. So you expect these things to appear in dimension 0, like in Morse theory. They don't, they appear in higher dimensions. But if you think of counting the critical points of a function as, roughly speaking, taking the Euler characteristic of a space, even when the critical points don't appear in dimension 0, they appear in higher dimensions, even when you get moduli spaces of higher dimensions, the Euler characteristic still makes sense. So it turns out there's something you can do. There's some difficult algebraic geometry which gives you a zero-dimensional virtual cycle. So that's the thing that the moduli space ought to be, even if it isn't. And you can think of it as the topological Euler characteristic of the moduli space. So it's not quite true. For starters, there might be a sign there, and there's something slightly more technical is true. But for the purpose of this talk, you can think of the DT invariant as just saying, take the moduli space of stable sheaves and take its topological Euler characteristic. And for the purposes of this talk, we'll just do that. In reality, it's something slightly more complicated, given by this formula of Behrend. But the complications in this formula all come out in the wash. Anything you can do for the easy formula, you can do for the complicated formula. So Behrend showed that actually the moduli space, at every point, you can assign a multiplicity to that point, telling you how singular the moduli space is at that point. And then you take the Euler characteristic weighted by that multiplicity, and that is really the DT invariant. So in particular, if the moduli space is smooth, this Behrend multiplicity is this sign, plus or minus 1 at every point. And so when you take the weighted Euler characteristic, you just get the topological Euler characteristic of the moduli space times by this sign. But yeah, for now, just the DT invariant is the Euler characteristic of the moduli space. If you think of it that way, you won't go wrong. So those are the original DT invariants of, God, nearly 25 years ago now. And then they were generalized. By the way, these are defined in any rank. This charge C can be in any rank. But we didn't allow strictly semi-stable sheaves. What Joyce and Song and Kontsevich-Soibelman did was work out how to generalize these invariants to get invariants when there are strictly semi-stable sheaves. So counting these are much more complicated because they have bigger automorphism groups. So roughly speaking, you want a sheaf to count as kind of 1, or its bare end function, towards the invariant. But if it has automorphisms, you want the sheaf to count as 1 over the Euler characteristic of the automorphism group, and that's 1 over 0. So you need some way to normalize that. And so you can see, here's one way you get semi-stable sheaves, is you could take stable objects of smaller charge and take their direct sums and extensions to get semi-stable objects of the original charge. And these have larger automorphism groups. You can think of this process as some kind of plathistic exponential, where you're replacing some bundle E of smaller charge by maybe E plus E. And E plus E has some symmetries, right? You can flip the two E's, so that's a Z mod 2, and that has Euler characteristic 2 factorial. So you can see this looks a bit like an exponential. N copies of E has the symmetric group on N letters acting, which has N factorial elements. So when you divide by that, it's starting to look like an exponential. Or, N copies of E, its automorphism group, if E is stable, is really GLNC. And by, its Val group is the symmetric group on N letters again. So you can see somehow something looking a bit like an exponential happening. And Joyce and Kontsevich-Soiberman found a clever way of taking something like a logarithm to invert this process in some sense and get more controllable automorphism groups. And I'm not going to explain it. But in that way, Joyce and Song were able to define a generalized invariant, which we'll call J of C, okay, which counts semi-stable sheaves. So stable sheaves and possibly strictly semi-stable sheaves. And it's a rational number, and it reduces to the ordinary DT invariant, the ordinary integer, when there are no strictly semi-stables.
Can I ask a question about this slide?
Yeah, of course.
So I'm familiar for instantons with including polystable points in the moduli space.
Yeah.
Is this the approach described on this? So the automorphism groups are then easy, right? It's just the
yeah.
So yeah, is the approach on this slide equivalent to just including the polystable points and then again computing the Euler characteristic of that moduli space?
No, unfortunately not, no. I mean, I'm focusing on the polystable ones in my description, but there are more general semi-stable sheaves. So iterated extensions of those pieces that the polystable guy is made up of. And yeah, the answer is no, it's more complicated. Anything I'm saying is some kind of toy model, and in reality, it's much more complicated. So unfortunately, you can't think that way. Sorry. But you can, what you say, yeah, you can't make sense of what you would like to be true, but you can think that way. That is just fine. Okay, so yeah, sorry.
So, I mean, you can still form a good moduli space, right? Of like either S equivalence classes of semi-stable guys or equivalently of just polystable guys.
Yeah.
So what goes wrong with trying to compute the Euler characteristic of that moduli space?
You could do that, but it just wouldn't be a nice, well-behaved quantity. It wouldn't, as you deform the Calabi-Yau, for instance, that number would just change. As you deformed the stability condition or the Kähler form, that number would change in a way that nobody knows how to control. Whereas the invariants I'm describing, we have a wall crossing formula for. So they just behave much better.
Okay, and so
you're losing too much information. You're ignoring all the extensions between these objects of smaller charge. And it's really important to keep that information in.
So like given an S equivalence class, it's clear what information about that class is important. like, yeah, if you knew the moduli space of polystable guys plus a bit of extra information at each of those polystable points, that's basically equivalent to this.
Yeah, that would be fine. If you knew, so if you're a polystable guy that looks like A plus B, if you know the extensions between A and B and the extensions between B and A, and maybe the super potential on their product, yeah, a tiny bit more information about A infinity product. Anyway, yeah, more or less, yeah, that would be enough information.
Okay, cool.
Okay.
Thanks.
So yeah, Joyce and Song were able to define these invariants. Kontsevich and Soibelman defined much more general invariants, refined invariants, motives, and polynomials, and so on, but subject to some conjectures, which Joyce and Song's works are unconditional. They proved the conjectures they needed in their case. Also, the Kontsevich-Soibelman conjectures are largely proved now. So it's possible one could use refined DT theory or Kontsevich-Soibelman's theory in everything that we do, but I'm not really expert enough on that. So I'm going to stick with Joyce and Song's invariants. So these are numerical invariants. They're rational numbers. And I just want you to think of them as being, roughly speaking, the topological Euler characteristic of the moduli space of sheaves. They're not quite that. The corrections you put in there are designed to make certain nice things happen. So one of them is that they're invariant under deformations of X. If I change the complex structure on the Calabi-Yau, I get the same numbers. And if I change the stability condition, like the Kähler form, for instance, then the invariants do change, but in a controlled way that we understand, called the wall crossing formula. So I want to explain the simplest possible wall crossing formula. And this hopefully will answer the previous question in some sense. You'll see where the extension data comes in. Okay, so suppose a bundle, say, sits inside an exact sequence like this. So it's got a subbundle A, a quotient bundle B. And let's suppose, because this is the simplest case, that A and B themselves are stable. So with this F is going to sort of decompose into A and B, but that A and B aren't going to decompose any further. So this is the simplest wall crossing formula. Okay, and now we're going to suppose we can vary the stability conditions so that the slopes of A and B cross. So, you might vary the Kähler form so the degree of A starts getting bigger and the degree of B starts getting smaller, and their slopes cross. So just below the wall, where the slope of A is less than the slope of B, F will be stable. And then just above the wall, where the slope of A is bigger than the slope of B, F will be destabilized by this exact sequence. So you have to, suddenly you throw F out of the moduli space, but extensions in the opposite direction become stable. So you include them in the moduli space. So you change the moduli space by throwing out F and putting in some extensions in the opposite direction. So let's see what happens to the invariant, the naive invariant. And this also happens to the actual invariant. So you lose the space of extensions from B to A. So if everything's a bundle here, then this is just H1 B dual tensor A, or HOMS from B to A. And the way the automorphisms act here, you actually get the projective space. So if you scale two extension classes, they correspond to the same bundle F. They give you the same bundle F. So you lose this projective space on this vector space of all possible extensions from B to A. And you gain the projective space of extensions in the opposite direction. So all those new bundles F primed, you gain those. Okay. So what does the topological Euler characteristic of the moduli space change by? Well, by losing this guy, you lose the dimension of this vector space here. That's the Euler characteristic of the projective space. And then by adding in this projective space, you gain this Euler characteristic. So again, that's the dimension of this vector space of extensions. And then by something called Serre-duality, that extensions x1 from A to B is x2 in the opposite direction from B to A. That's because we're on a Calabi-Yau. And so what you end up with is this alternating sum of X groups or dimensions of X groups between B and A. And this is the entire alternating sum because the HOMs from B to A vanish. That's because A and B are stable at the same slope on the wall, so they can't have any HOMs between them unless they're isomorphic to each other. And I'm assuming they're not. I forgot to say that. And therefore, there's no X3 bisexuality, and there's nothing else. And so what you find is these extension groups or dimensions of these extension vector spaces, you can't control these. You have no control whatsoever over X1, but you have complete control over their alternating sum. That's given by a Riemann-Roch formula or an index formula. And that's given by the what's called a Mukai pairing between B and A. That's the integral of the Todd class of X against the Chern character of A times the Chern character of B dual. So this is topological. So the change in the moduli space, in the Euler characteristic of the moduli space, we can control. It's entirely topological. We can't control what we lose and we can't control what we gain, but the difference between them is given by a topological number. And so what happens to the invariants is that the invariants counting sheaves in class of F, so this would be, the square brackets just mean the charge of F, so this is like J plus of C. So the DT invariant above the wall is the DT invariant below the wall, plus this topological number, and then times by, I only worked at 1F, at 1A and 1B. Now I can vary the A's and the B's throughout their own moduli spaces, and I get a product structure. I get this computation can be done over the moduli space of A's times the moduli space of B's. So when I just did the computation at a point, when you then allow A and B to vary, you get the Euler characteristic of A's moduli space and the Euler characteristic of B's moduli space. So you end up with this formula. And so this is the simplest possible wall crossing formula. And what's important about it is it just tells you the way the DT invariant varies as you cross the wall. And the variation is entirely the coefficients are entirely topological, kind of universal. And then the corrections are given by DT invariants of lower charges of the pieces that my sheaf F might split into. And then there's higher order wall crossing formulae. So this wall crossing came from essentially a filtration of F with one piece, just an A in there, and then B was the quotient. But you can have much longer filtrations with N pieces. So you could have an A1 and A2 and so on, all nested, all sat inside each other, and sat inside F. In other words, you can split, your F can split into a whole direct sum of many pieces. So the graded pieces of this filtration. And what happens then is you get higher order terms here, where if you're looking at the contribution from F splitting into 3 terms, you'll get something just like this with topological universal coefficients, and then a cubic in DT invariants of smaller charges. You'll get a JA, JB, and JC. And if it splits into 4 pieces, you'll get a quartic and so on. But they're all of the same rough shape. So this is the main tool that we use, is this wall crossing formula. So are there questions about that?
This is going to give us something that we could recover from the Kontsevich-Soibel wall crossing formula, right?
Yeah, so the Kontsevich-Soibel wall crossing formula is just a fancier version of this for refined invariants. And it's, written in a clever algebraic way, because it gets much harder to write these terms out when you get cubics and quartics and so on. And their way of writing it, of course, is much slicker. But yeah, it amounts to the same thing. Okay, so all you have to take from this is the way DT invariance changes with change stability condition is controlled. To leading order, there's no change, and then you get these kind of lower order pieces, which are quadratic, cubic, and so on. And they're DT invariants of smaller charges in some sense. What you mean by smaller is obvious here. Sort of A and B have lower rank than F. but it won't be obvious in the cases we're going to work in, where we're not just dealing with sheaves and subsheaves. But what you mean by smaller will be very important in what we do. Okay, so here's the rough idea of what we do. We twist up all our sheaves to be very positive. So we twist them by very ample line bundles so they have no higher cohomology.
Just a question. The previous slide, did it depend on the choice of stability condition at all, or this is just a matter of counting objects with any stability condition, right?
No, sorry. So here, when we cross the wall here, my notation is that J plus is counting of stable objects above the wall. So for the wall is in the space of all stability conditions, and J plus is just above the wall. So I'm using a stability condition where the slope of A is just slightly bigger than the slope of B. And J minus was below the wall, so that was where the slope of A was just slightly less than the slope of B. So those are counts of sheaves for different stability conditions.
Yeah, no, what I meant is, I think in physics, there's one stability condition that makes sense, which is the pi stability condition, and everything else is some imagination, no?
but there's many pi stability conditions.
Sure, as you vary parameters, you get many pi stability conditions, absolutely.
Yeah.
But this does not hinge on what kind of function mu is, like on K-theory classes, right? It's, yeah, you can put any function, this will still be true. Is that correct?
I'm not sure if I've understood the question, but in pi stability, you have parameters and you can vary those parameters. And that, as you vary the parameters, the slope of some object A may change, it may cross some other object B. And that's what that's all I'm doing here. So
okay,
slope here would just be the slope of Douglas's central charge.
Let me try to ask a question.
Yeah.
Let's see, would it make sense? Do we know that on a Calabi-Yau threefold, with the family of stability conditions that comes from high stability condition, that wall crossing invariants actually have this property, that they will jump in this way, that this is sort of the right structure. Does it make sense?
Yeah, it does. It makes perfect sense. Well, I think it makes sense. I'm not really an expert on pi stability, but I'm going to assume it's the same as Bridgeland stability. Because certainly Bridgeland stability was invented to try and model pi stability. And then that's correct. We have such a wall crossing formula for Bridgeland stability conditions. Yeah. So that's exactly what you should be thinking of. You should be thinking of mu here as just being tan of the angle of, the slope of the central charge in some pi stability condition. And now you vary the pi stability condition and make the slope of A and the slope of B cross each other. And then this kind of formula will happen. Okay. So yeah, here's the rough idea. So ignoring the first step. So we twist everything up. We just assume it's all nice and positive, has no high cohomology. So you can ignore that step. So now we just do something incredibly simple. We replace our sheaves by co-kernels of sections. Okay, so if I take a section of my sheaf E, I can take the co-kernel, the quotient by that section, and I just get some sheaf of lower rank. Or, if it's a vector bundle, I get a section, I get a vector bundle of lower rank away from the zeros of that section. Near the zeros of that section, I get a singular vector bundle, which is all that a coherent sheaf is. Okay, and it's a sheaf of rank 1 lower, and we know what its charge is. And so to a first approximation, let's just suppose that everything here is stable whenever the section is non-zero. This is certainly not true, but let's suppose it is. then what you find is, because this n is very large, amazingly, you find that all the f's come from an e plus a section. So any stable f that you can find of this charge here is the quotient of an e by a section. Okay, so the data of e and s is the same as the data of f. Given an e and an s, you can produce an f. Given an f, you can find an e and an s. They're unique. They're the same. They're the same data, up to scaling the section by a constant. So what you actually find is that the moduli space of f's in this charge here is just a projective bundle over the moduli space of e's, where the dimension of the fibers is given by this topological number, which is the number of sections of E. So what you find is that the DT invariant counting Fs, the number of Fs, by taking Euler characteristic, is just the Euler characteristic of that projective space. So that's this topological number n, times by the Euler characteristic of the base, so the DT invariant counting the E's. So what you end up finding is just what we're after. We've just expressed the DT invariant in rank R, say, the DT invariant counting E's, in terms of the DT invariant of lower rank counting the F's. Okay, so that's if, you know, all our fantasies came true and there was no stability problems. And if this looks a little bit like a wall crossing formula, maybe it doesn't yet, but it is. We will see that shortly. And that's when we'll answer Mina's first question. And now what we're going to do is wall cross to handle stability and make this sort of fantasy come true. And when we do that, we'll get all kinds of corrections. And they'll be in some sense of lower order terms, and we have to make that precise. And that's where we'll get a complicated induction going. So this sort of fantasy rough idea works perfectly in rank 1, so I can just tell you the answer there. So in rank 1, I'm interested in moduli spaces of ideal sheaves. So these are just up to tensor by a line bundle. This is just the trivial line bundle, the trivial rank 1 line bundle on X, but with singularities along some subscheme, so some curve or points in X. So here, the DT invariant, so this is usually what physicists call DT invariant. This is the rank 1 DT invariant. This just counts subschemes or subcurves of X. But if we apply this procedure to it, what do? We take a section of that rank 1 sheaf, twisted up by n, and then we take its co-kernel. So what is such a section? Well, really, it's just it's a section of this line bundle ON which vanishes along Z. So in other words, it's the section of a line bundle cuts out a divisor. So it's a divisor, a codimension 1 subvariety of X, which contains our curve and points Z. Okay, and then what it works out is when you work out what its co-kernel is, what this F is, which has rank 1 lower, it's got rank 0. So this is some rank 0 sheaf. It's generically 0 on the Calabi-Yau, except along this divisor where it's some kind of Dirac delta. It's just the trivial line bundle on the divisor, but then with singularities along this Z, this curve or curve and points inside X. And so we express that this way. So it's the push forward of the ideal sheaf of Z on the divisor, pushed forward to X. So it's made 0 on the rest of X. Anyway, so this is what I believe physicists call a D40 to D0 brane. And in this case, it turns out that for n large enough, for starters, all these ideal sheaves are stable. There are no semi-stability issues. They're Giesecke stable, they're slope stable, they're any stable you like, pretty much. And they're the only stable sheaves of this form. The F's, any stable F in its moduli space is of this form. So it is the co-kernel of a section of an ideal sheaf. And so what you find is that the moduli space of F's is just a projective bundle over the moduli space of E's. Okay, so what this says is that counting the D4, D2, D0 branes is precisely given by counting the curves and points in X, so the rank 1 DT invariants. This is only for n large. Okay, for n small, this would fail. So for instance, if your divisor, if instead of taking your divisor to be in this, to be of degree n, you could sort of take a divisor of half the degree. And then instead, you've got two things you could do. Either you could thicken it scheme theoretically, so you could sort of take twice the divisor by thickening it in the direction of X. That would give us one of these sorts of sheaves that we are counting, one of these Fs here. Or you could take a rank 2 bundle sat on that divisor. And what this theorem is saying is that will always be unstable. The second possibility would never count so long as n is very large. It will never happen. You'll always get something unstable. So really some miracle happens here when n is large, and you get this very simple relationship. Nothing can go wrong. All these sorts of things that you might imagine might happen, all these other possible stable or unstable bundles, they just don't occur. And you get this very simple relationship between rank 1 DT theory and rank 0 DT theory.
There should be something very special happening always, even if your n is not very large, just simply because D6 brane has such huge central charge. So it's. I mean,
so where does the D6 brane lie?
Crossing essentially predicts that if you have an object that has a very large central charge itself, then all the possible wall crossings with it are extremely simple. It predicts a simple formula. It's some kind of simple conjugation. A formula that's much simpler than anything. So there should be a more general simple formula that's true even.
So
I mean, your formula is somehow geometric, right? Like it's true when D4 branes are nice and big and heavy, but there should be something that's true even if you add the orbital. But you have a large heavy D6 brane on an orbital, say. So
if the D4 brane is not big and heavy, what is big and heavy? Why?
The D6 brane. The line bundle on X is heavy.
So even though the D6 brane has only got rank 1, why would? What, you just mean it's bigger than the D4?
Oh, its central charge is infinite, right? If on a non-compact space, it'd be infinite, right? Even on a quintic, right? It's as long as it's like the heaviest object, it's mixing with everything else has to be very simple.
Okay. So that's in some kind of large volume limit of the stability condition? Right. Okay. Yeah, thank you. Okay, so let me just briefly mention as a digression, we had this formula on the last page relating rank 0 DT to rank 1. So these Abelian DT invariants, the rank 1 guys, count curves and points in X, and then by this Malik-Nekrasov-Kunkov-Pandra-Panda conjecture, they can be written in terms of Gromov-Witten invariants of X. Whereas, so that's the right-hand side. At the left-hand side is this generating, you can form a generating series of these guys. And then S-duality predicts they're supposed to give you modular forms. So here are some of the references. You guys probably know, or half of you guys know those references better than me. And then I won't have time at the end, but in one of our papers, we discuss how to see this modularity, this predicted modularity, entirely geometrically using something called Noah to Lefschetz theory. But anyway, the point of this slide is just to emphasize that although in the physics literature, I'm not sure this has been considered, certainly in the maths literature, this has not been exploited. The fact that this S-duality should make predictions about rank 1 DT invariants and Gromov-Witten invariants and could maybe constrain Gromov-Witten invariants. That hasn't really been explored in maths. So we have some discussion about that in one of our papers. But that's really a digression. I'm more interested in higher rank DT invariants in this talk. Okay, so I kind of explained the rough idea. I've explained wall crossing. Now I want to explain how they come together. So in higher rank, the rough idea doesn't work so nicely. You get corrections. So you end up writing rank R invariants in terms of invariants of rank R-1 and lower. So you get the wall crossing generates all this kind of shrapnel that comes off, and you have to count that as well. And I'll explain roughly how we do that in a minute. And then inductively, we can apply this again to the rank R-1 and below invariants. And eventually we get down to rank 0. So we end up proving in one of our papers that a DT invariant in any high rank can be written as a universal polynomial in terms of DT invariants, all of rank 0. And they're rank 0 and really pure dimension 2. They're D4, D2, D0 branes. They're really counting sheaves supported on surfaces in the Calabi-Yau threefold. And this is some countable list of invariants here. So there's some polynomial in infinitely many variables, but all but finitely many of the coefficients vanish in any given situation.
Just to make sure I understand, your rank is the number of D4 branes or D6 branes?
The rank is the number of D6 branes. Yeah.
R is the number of D6 branes. Okay.
Yeah. Yeah. Okay.
No, sorry. Can you just slow down?
Yeah.
D4, D2, D0 are not counted by Gromov-Witten theory. I didn't understand something. The D2, D0, of course, are, but not D4 branes.
Sure. So, but I'm just saying, because of our results here,
yeah,
that we managed to express. These are the rank 0 guys. So these are the guys. These are the D4, D2, D0 invariants. Yes. And we express them in terms of the rank 1 invariants,
sure,
where there's one D6 brane. So the right-hand side is expressed in terms of Gromov-Witten theory. So we're claiming that there's such a relation.
I see.
So yeah, we're claiming that Gromov-Witten invariants can be related to these D4, D2, D0 branes, which should be governed by modular forms.
Okay, and then we're going to start increasing the number of D6 branes.
Right, okay. Exactly. Yeah. Okay, so this is the first result, is that arbitrary rank, any rank DT theory with any number of D6 branes can be expressed in terms of these D4, D2, D0 branes. So they can be expressed in terms of rank 0 DT invariants. Okay, so they can be expressed in terms of these modular forms conjecturally. Okay, but so that's one of our results. But what we really wanted to do is express everything in terms of rank 1, the Abelian theory and Gromov-Witten theory. So what that leaves is to express rank 0 DT theory in terms of rank 1. And for that, I will come back to that at the end. So we'll actually do our procedure again and go via rank -1, but I'll explain what that means at the end. Okay, so what I'm going to do now is try and explain some of the technicalities of how we do the wall crossing to prove results like this. So what goes wrong with the fantasy idea and what the corrections are. So this gets a bit technical, so you can kind of, I'll go a bit faster maybe, but you can slow me down if you're actually interested. If any of you are experts on stability conditions, then that's great. I may not be able to answer your questions. Okay, so we're going to use something called weak stability conditions. So these are not Douglas pi stability, but they're closely related in various limits. And they're going to depend on 2 parameters, B and W. And unfortunately, there's this technical thing. We're going to work in a certain Abelian category. So this is, we're not working just with pure coherent sheaves, although some coherent sheaves sit here. We're working with certain 2-term complexes. So these would be sheaves, E-1 and E0, with a map between them. And these would be the objects we're considering. So for instance, E minus 1 could be 0, and then we would just have a sheaf. And they satisfy various conditions on their standard slope, their Mumford slope. But anyway, I wouldn't worry about this. We're working with certain complexes of sheaves. But those complexes of sheaves will, examples of them will include the actual sheaves that we care about. And then there's the central, yeah, sorry.
Being some category of stable objects or semi-stable objects? Or does it have any physical meaning, the choice of that category?
Yeah. What is the physical meaning of that? It's the objects which can be made up of, which are, I don't know, bound states or something, of any number of semi-stable objects whose phase ranges from 0 to pi. Is that any use to you? Yeah. So imagine taking all pi stable objects whose phase lies between 0 and pi, and now taking all possible extensions of all those guys. So they may not be stable, but their phases never get out of this interval from 0 to pi.
Right.
That's this category for an appropriate, for appropriate numbers. Okay, and then we have a central charge, and you're not supposed to look at the formula. The point is just that it's the usual thing, it's topological. It only depends on the charge of E, its Chern character, and it's given by some slope-like formula. Okay, so you end up with a slope function as usual, and this is the formula. It's really not relevant what the formula is. What's relevant is it's topological, and it depends on two parameters, B and W, and we're going to vary B and W. We're not going to vary H. We could do, we know how to control that, but for us, we're just going to vary B and W and see how stability changes. All right.
And why do you get only two-term complexes?
We impose that from the start. That's what we're going to consider, because essentially this rough idea I was using before here, where I take I'm interested in sheaves, so they're one-term complexes, but I'm also going to be interested in a section of that sheaf and then sticking these two together to produce an F. And that's why I'll want two-term complexes. And I really don't want any more than that. So we just impose that condition. And it turns out that these guys, Macri-Toda, actually managed to produce something called a weak stability condition on this precise category. So there's a lot of stuff we can use. Yeah, it's a bit hard to motivate, but it turns out it's the right thing to do for the problem we're considering.
So it's not the case then that your results hold for any Bridgeland stability conditions. It's only for the subset, this Macri-Toda subset of stability conditions. Yeah,
that's correct. I mean, almost certainly you can do what we're doing in some space of Bridgeland stability conditions as well. But the induction would be harder. You'll see the induction later. But yeah, certainly our results don't cover that. Yeah, that's completely correct. Okay, and then we use heavily this Bogomolov-Giesecke inequality conjectured by Macri and Toda. And this has been proved in some cases now. So what this is if you know some of you will know the standard Bogomolov inequality. So what that is it says if you take slope stable sheaves or Hermitian-Yang-Mills connections, they're defined using only the first Chern class or first Chern character, because they're defined using ordinary slope, so degree of the first Chern class and so on. And yet the Bogomolov inequality tells you that their second Chern character is positive or negative. I never get it right. Okay, this is very similar. We're using the first and second and zeroth, so the rank Chern characters in our slope here. And the conjecture is that actually for the stable guys, that determines a certain bound on their third Chern character. Okay, and you know, there's the inequality. You should ignore it. But it says that semi-stable objects for our stability conditions should satisfy a certain inequality. And as I say, it's proved in certain cases. It was invented because it turns out that when it holds, you can prove the existence of Bridgeland or Douglas pi stability conditions. Although we barely use such stability conditions at all. And it has been proved for some Calabi-Yau threefolds, but it's not proved in general. And I don't know if physicists have a point of view on this inequality or have even seen it actually. But anyway, it's a technical device and we use it heavily. And you should ignore it. Right. What I want to explain is sort of the geometry of this wall crossing. Okay, so you have to plot some pictures. So here's what we plot. So we plot the slope of our charge, our class E, and its second Chern character on the same axes as our B and W. Okay, and the reason for that is we end up with a picture like this. So firstly, the Bogomolov inequality means that whenever E is stable, this quantity here that we're plotting is always outside this parabola. Whereas the stability conditions, B and W, all lie inside the parabola. That was because right at the beginning, I told you that W had to be bigger than B squared over 2. And the picture is as follows. If you have some class, some charge C or some object, some bundle sheaf or complex of sheaves E, and you have a stability condition, B and W, then you should draw the line between them. And if pi of E becomes unstable or semi-stable at this stability condition, B and W, then it'll actually be unstable all the way along this wall. So I can move B and W always along this wall, and the slope of E won't change, and its semi-stability won't change. And the slope of this wall here, of this line joining B and W and pi of E, is the slope of E. It is this quantity nu, this quantity here, nu BW of E. So this is the way we're determining the slope. Okay, so if you plot these quantities in this way, that determines that the slope of E is given by the slope of the straight line joining B and W to pi of E. Okay, and so what you find is for most B and W, there'll be a wall and chamber structure. So for most B and W, as you move around in the chamber, the stability of E won't change, and then suddenly you'll hit one of these walls where some other F has the same slope as E. Okay, so if my B and W were down here below the wall, then by drawing the line to pi of E, you would see that F had a completely different slope from E, and so it wouldn't be involved in a wall crossing. It wouldn't be destabilizing on one side of the wall and not destabilizing on the other. But for these special walls, where B and W lies on a line joining two classes like F and E, then what you can find is that on this wall, the slopes of E and F are the same. So below the wall, E might be stable, and above the wall, it might be unstable because F might have destabilized it. So that's the kind of rough picture. And then something slightly less rough is this picture. And this is roughly what goes on in our paper. Okay, so we study this class Cn. This was actually the class of F. This was the co-kernel of those sections. I'll remind you of this in a minute. It lies down here somewhere. And then we just analyze all the possible walls for this class. And you get this wall and chamber structure. So if your B and W are not on a wall, if they're in the gray area, then as you move in that chamber, the stability or instability of your sheaves F does not change. And then as you cross one of these walls, there'll be some other class down here, which is also on that wall, which may destabilize you as you cross the wall. And then there's sort of three features. At the bottom, there's a special wall. It's not really a wall. There's a special sort of boundary, the Bogomolov-Giesecke boundary, where below this boundary, everything has to be unstable. Below this boundary, that Bogomolov-Giesecke inequality is violated. So there can be no stable objects of class Cn. So there's no Fs down here. The moduli space is empty and the DT invariant is 0. Then there's a special wall that we call the Joyce-Song wall. That's the line joining our class to the class of the line bundle O minus n. So that'll be the line, that'll be the wall on which our class can get destabilized by these sections I've been talking about. I will remind you about that in a minute. Then there's some other walls. Again, it's very hard to control these walls, but there's only finitely many. And then there's an upper wall, and beyond that, we're in what we call the large volume chamber. And here, everything is a sheaf. Every stable object is a sheaf. We understand it. It's basically, it's almost Giesecke stable. It's actually something called tilt semi-stable, but that's halfway in between slope semi-stable and Giesecke semi-stable. It's something we understand. And then from here to wall cross to Giesecke stability is something rather easy. So more or less, the game is to go from the bottom to the top, to go for, you know, at the bottom we know how to compute everything is 0. At the top, we get the invariants we want. They're basically the DT invariants, and we have to see what happens in the middle. The interesting case is the red wall. That's where our fantasy picture, that rough idea slide, that's where that happens. And then all the other walls, they're where kind of corrections appear and shrapnel appears, and you just have to control those with some induction. Okay. So the Joyce-Song wall is where the slopes of our F and this sheaf O minus 1 are actually the complex where it's been shifted coincide. So let me say what happens on this Joyce-Song wall. What happens is basically that exact sequence I gave you at the start. So remember, we took an E, we took a section, and we took its co-kernel. That's not quite what happens. What happens is in the derived category, you can rotate this triangle. So you can put F in the middle. You can have E on the left as if it was a sub-object, even though it's got higher rank. And you can put a shift of O minus 1 on the right. So that means the complex where O minus 1 is no longer in degree 0, so it's no longer a sheaf, but it's in degree 1, minus 1. So it's been moved to the left. So it's sort of a minus D6 brane. Yeah. D6 brane, D6 is minus 1. Okay, so you can think of it, instead of thinking of E as being O minus n plus F, you can think of F as being E minus O minus n. But that's the same as thinking of F as E plus minus O minus n. Okay, so that's what this shift does. It sort of changes the charge to minus, I don't know, brane to anti-brane or something. Okay, and what you'll find on that red wall there, this is what destabilizes F. You find that F can be destabilized by this crazy exact sequence where its sub-object actually has higher rank and its quotient object has negative rank. And this is a sort of minus D6 brane. And so this is finally the answer to Mina's first question. So we really want to cross this red wall. So we really want to consider these crazy stability conditions where you can be destabilized by a sub-object, which is not a sub-object in a way you would normally think of it. It actually has higher rank, but in these crazy stability conditions or crazy abelian categories, it is a sub-object, and the quotient object really has negative rank. Okay. And then we do the wall crossing across this wall, and the formula will give us the formula we want. Okay. So let's see what the wall crossing formula gives as you cross this red wall. If you remember that sort of introduction to the simplest wall crossing formula I described, that would say the number of Fs above the wall, that's this quantity, equals the number of Fs below the wall, okay, plus, what was the plus? What was the correction? It was Firstly, this n is the number of, it was the alternating sum of dimensions of extensions between this guy and this guy. Okay, but that was just the number of sections of E twisted by n. Okay, and that was this quantity here, n, capital N. So this is some topological quantity. So that roughly governs the number of extensions between these two things, which is just the number of sections here. All right, and then times by the DT invariant counting this guy. Well, that's just one. There's only one of these guys. And the DT invariant counting these guys. And that's the DT invariant in one rank higher. That's the rank R DT invariant. This is the rank R minus one DT invariant. And then there'll be higher order corrections coming from more complicated destabilizing things. Okay, but this is precisely our formula that we had on the page where we said, you know, the rough idea. This is the formula you get from saying that, roughly speaking, the space of F's is a projective bundle over the space of E's, with fiber given by the projective space of all sections here. That was this formula here. But now the formula is more complicated because there are these dot, dot, dots. And the dot, dot, dots come from sections which factor through not just E, but maybe some part of E, so some semi-destabilizing subsheaf of E. But that has lower rank. And so there's hope of inducting here. There's some hope that even though sub-objects aren't subsheaves, even though you can have negative rank and so on, there's some hope that these corrections all correspond to lower rank invariants. And that's what we need to prove, and that's what we do. So, okay. So, crossing the red wall gives you this formula. This is the key formula. The three terms I've written there are the things we want. The dot, dot, dot is the shrapnel that we don't want, but we have to control. All right. And so what do? Once we've got this formula and we know something about the shrapnel, we then we wall cross all the terms above the wall. So that's this one, W plus, and and this one. That's W on the wall. We wall cross those all the way up to the large volume chamber, where we can get standard DT invariants instead of these crazy DT invariants and strange stability conditions. And this term below the wall, the Joyce-Sung wall, we wall cross that down to below the Bogomolov-Giesecke sort of boundary, where it'll become 0. So we'll end up with a formula expressing rank R minus 1 DT invariance in terms of rank R DT invariance plus a load of shrapnel. That's the rough idea. And then the technical aspects of the proof are that we prove that all these wall crossings involve only sheaves. Okay, so it's only the Joyce-Sung wall where we get this fancy stuff where you have complexes of sheaves. I mean, you have, anti-branes. Every other wall crossing that appears for any of our objects or any of the objects that get generated by the shrapnel, any of the sub-objects that sort of get spat out at each wall crossing, we prove that every single wall crossing for any of those involves only sheaves. Okay, so it's only the Joyce-Sung wall which gives more elaborate objects. Okay, so these wall crossing pieces in turn spit out only destabilizing pieces of lower rank, which also we then also wall cross those up to the large volume chamber or down to the empty chamber at the bottom. And their wall crossing also involves only sheaves. Okay, so you can see that the rank kind of wants to decrease at every stage, which would be good. It would allow us to induct. But actually, it can also involve rank 0 sheaves. And so actually the other piece then might have the same rank that you started with. So if you've got a rank R sheaf, as you cross a wall, we prove it'll only be destabilized by sheaves of lower or equal rank. It might be destabilized by another rank R sheaf and a rank 0 sheaf. Unless you're on the Joyce-Sung wall where you get these fancy complexes. But again, at each stage, we prove that even if the rank stays constant, some other topological quantity always decreases. So whenever you split into 2 or more pieces, this quantity here called the discriminant always gets smaller in the piece. The discriminant of the pieces is always smaller than the discriminant of the thing you started with. So that means we can do another induction on that quantity as well. And by doing a double induction on both of those, it turns our formula, which is here, into this formula here. So we've managed to take W plus up to infinity. We've taken W minus down to minus infinity where there are no sheaves, so we get 0. We've managed to take this W up to infinity, and then all the shrapnel that's produced, we can prove it has lower rank. Okay, so that's all. That's what happens. It's pretty hard to control all these things, but that's the final upshot. And then a further wall crossing passes from this large volume limit tilt stability to Giesecke stability. And so we end up proving that the DT invariant here of rank R can be expressed in terms of DT invariants of lower rank. So there's one of them. That's the F. So this is counting the E's, this is counting the F's. And then here's the others. All these lower order terms are horrible, but we know they have lower rank. They're universal formulae in DT invariants of lower rank. And so now we can do another induction on rank and get all the way down to rank 0. Okay, and then the last thing I'll talk about is how we go from rank 0 to rank -1. But I'm sure I've sent most of you to sleep now, but the idea is pretty much the same. We just go one for...
Something.
Yeah.
In your construction, I mean, negative rank isn't physically exotic because, you know, if I have a D6 brain, I definitely have the anti-D6 brain.
Yeah.
The only thing that would be exotic if someplace in your space of choice of ability condition, they're both stable simultaneously, and you're at large radius. That would be really strange. But you don't have that.
Well, we can have them. We can have a D6 brain and an anti-D6 brain stable at the same time, but yeah, not of the same phase. Like one would have phase. If one had phase pi, the other one would have phase 0 or 2
Yeah,
pi.
but so they're never together in your Abelian category.
That's correct. Yeah, absolutely correct. Yeah. Okay, so the last thing is, suppose now my E has rank 0, then we just do the same process again and go to rank -1. Okay, so again, I twist up, I assume E has no high cohomology. I take a section, and now what I do, instead of taking the co-kernel of this section, I just take this complex here. So I take the section and I form this complex. So E has rank 0, this has rank 1, but you know, in terms of the complex, this is in degree -1. I moved it over here. So this is like an anti-D6 brain. Okay, so this has rank -1. So we have rank 0, rank -1. So we end up with a rank -1 complex of sheaves. And we can't take the co-kernel because this S isn't injective, so it wouldn't make sense. This has kernel and co-kernel. So this is really a non-trivial 2-term complex, which is made up of sort of anti-stuff and real stuff, a sheaf minus a sheaf. All right, and we consider these complexes. And we just do what we did before. We just ignore the fact they're not really sheaves, they're complexes of sheaves, but more or less something similar goes through before. There's a joist-on wall where this O minus N, this line bundle here, has the same phase as the F and the E. You get the wall crossing as you go over that wall. And then over all the other walls, you need some control, just as before, to control all the lower order terms. And the control is given by this result. Before, the control was whenever you went over another wall, all the pieces had lower rank or lower discriminant. The control this time is that as you go over other walls, all the pieces are actually just of more or less the same form. They're also rank -1 complexes and rank 0 sheaves. So they're more or less F's and E's themselves, but of lower charge. In what sense? It's in the sense of this degree. So this is what replaces the discriminant now. So the rank 0 sheaves, whenever you have a wall crossing and they split up, they always split up into things of smaller degree. So you get rank 0 sheaves of smaller degree This is just the, you know, the size of the support, the surface size of the surface they're supported on. That gets smaller at each stage. And there's no other ranks. No, rank -2 doesn't appear. Rank -2 doesn't appear. Rank 1 doesn't appear. So this is what gives us the control in this case. I don't know what went off the bottom there. That wasn't supposed to be there. Ignore that. Okay, so what we end up doing is proving actually that an induction on this degree here means we can prove that rank 0 DT invariance can be expressed in terms of rank -1 DT invariance, counting stable rank -1 complexes of a certain type. And then it turns out that when you dualize these complexes and shift them by 1, you make them into rank 1 complexes. And after doing a further wall crossing, you prove they become something called a stable pair. And so after a further wall crossing it's 10 years older, due to Bridgeland and Toda, it then becomes an ideal sheaf again. So this is a rank 1 ideal sheaf that we were describing before, which just counts essentially Gromov-Witten invariants. It counts embedded curves actually in my Calabi-Yau threefold. So I've skipped lots of details here, but it turns out that by dualizing and then shifting these rank -1 complexes, you can get back to rank 1 ideal sheaves and rank 1 DT theory and Gromov-Witten theory. So the rough idea in this case gives a simple universal formula relating rank 0 to rank 1. There's the opposite. I don't want to confuse. Earlier, I told you how to go from rank 1 to rank 0. This goes in the opposite direction. This is from rank 0 to rank 1. It's not the inverse of what we did before. It's something different. Okay, so the upshot is finally we've expressed all DT invariants counting arbitrary rank sheaves in terms of either rank 0 DT invariants or rank 1 DT invariants, depending on what you prefer. Rank 0 DT invariants should be governed by some modularity, so that's nice. Rank 1 DT invariants should be governed by Gromov-Witten invariants, so that's differently nice. And I'll stop there. I won't discuss the Noether-Lefschetz stuff.
So physically, the idea of this reduction from E to F, this F is basically, is it right that F is basically the bound state of E with an anti-D6 brane and a huge number of D4 branes?
Yeah, correct.
And so the point is that that bound,
because there's so many D4 branes, you can prove just some magic happens, and you can prove that all or almost all of those bound states, sorry, almost all of the stable objects in that class are similar bound states. They can all be written as bound states.
Mm-hmm.
Would this apply to a non-compact Calabi-Yau, like, I don't know, O-3 over P2 or something?
We have no idea about non-compact. Yeah, we can't say anything.
So for such non-compact Calabi-Yaus, you have a very good description.
Of
well,
what?
You certainly know the DT theory. You also...
You know the rank 1 DT theory. I don't know that you know higher rank.
Well, you know a lot of things. For example, near the orbifold points, you actually know arbitrary rank as well, because near the orbifold point, the whole thing is described as a modular space of quivers.
Right.
Quiver representation.
Yes. Yep.
So firstly, does this? Yeah. So I want. You must be able to apply. Hopefully, have you elsewhere understood how to just count D4 branes on P2?
No.
Is this known? D4, D2, D0 on P2? Say.
I should know this. Yeah, I mean, that's essentially the Vafa-Witten theory of P2, right?
Yeah.
So, yeah, so not me, but yeah, I mean, Pialine and, you know, Mancho and people like that, yeah, they know a lot about that problem. Yeah. Yeah, so that's going in the direction of actually making these formulae, you know, explicit and getting nice formulae. With, you know, our work gets nowhere near that kind of thing. You know, our formulae are just abstract existence theorems. They're not. You would never try and do what we do to get actual formulae. But yeah, if you work in non-compact and toric situations, then there's a hope of getting really nice formulae, and people are beginning to do that.
There, the difficulty, from what I recall, was that, well, you can do any calculation you want at an orbital point, essentially anything. Certainly for rank 1 DT theory, you could do any calculation. And it's known thanks to, I don't know, works of Reinecke and people who study modular Hoover representations. The trouble of understanding anything at large radius was that there are infinitely many walls, and somehow, and controlling that sequence of infinitely many walls was a very difficult thing.
Yeah, yeah, absolutely. Yeah, I completely agree. And the beauty of these weak stability conditions is we can prove there's only finitely many walls that we have to handle, so it makes things easier. Yeah.
Do you think it's realistic you're going to get some formulas out of this?
Not out of this. I don't. I think this is just motivation to now look for formulae. I think. I absolutely think there will be formulas, but not by this method. That's my feeling. Yeah. Yeah. So there's a paper of Zabzin, Nekrasov, Piazzalunga, another guy in Durham, whose name I've momentarily forgotten, sorry, where they compute some kind of higher rank topological vertex. Has this got a playing with the index of M theory or something? And there's some mathematicians as well who do the similar thing around the same time. So they're getting nice formulae now, and they're also seeing similar things that in their setup. So this is in toric case, that the rank R theory is determined by the rank 1 theory. But that's a very different theory that they're considering to this here. But it's clearly going to be related. So yeah, I'm sure there will be formulae, but not yet. When I was talking about the Vafa-Witten theory of P2, the name I forgot was Alexandrov, I think.
Do we have any further questions?
Can I just, I have one rather specific example, which I was just curious if you thought it would be feasible to make progress on this. There are these papers by Malik and Oblomkov from where they compute the DT and rank 1 DT invariants of ALE times T2.
Yeah.
And so for a very nice case like that, do you think that these methods would allow one to get the higher rank and at other points, at all points in stability space?
I would not advocate using these methods there, but I would certainly encourage calculating there. So, in rank 1, these ideal sheaves are more or less the same as points of the quat scheme. So you can say they're the same as a rank 0 sheaf with a section. Is that what I mean? Yeah. So the ideal sheaf is the same as taking the structure sheaf of your subscheme with the section 1 and thinking of the ideal sheaf as the kernel of that. So expressing the ideal sheaf as the kernel of a certain quotient, that generalizes to higher rank. So instead of counting higher rank bundles on one of these ALE spaces, what you could do is count higher rank quotients. So you would take, you know, R D6 branes or R copies of the structure sheaf, and you would take quotients to some other sheaves. That is the kind of thing that Nekrasov and others were studying and have a higher rank vertex for. So it's not quite counting of sheaves like I'm describing, it's counting certain marked or framed sheaves or quotients. I think that problem would make a lot of sense over an ALE space. But in general, counting bundles on non-compact spaces is not a sensible thing to do without some kind of framing. So you need to handle the framing in some way, and then stability becomes more complicated. So yeah. So I would certainly encourage calculating that case, but not using our methods.
Okay.
Yeah, thanks.
All right, any more questions? Okay, if not, let's thank Richard again. I think it's late where you are, right? What time is it there?
Yeah, my kids will be in bed. It's 10:30. Is it? No, it's 9:30. I hope. The clock's changed, so I'm very confused. Yes,
Oh,
9:30.
okay. Well, I'm sure you're still on the old time. All right.
Yeah, thank you. Thanks very much.
Thanks for coming.
Yeah,
I look forward to seeing you in Berkeley next year.
Yeah, absolutely. Okay.
Great. Bye.
Okay. Bye, everyone.